The new section is entitled Exact Equations. Of course, I mean differential equations. When is a differential equation exact? If you're given an equation that looks in this form, you have a function of x and y times dx plus another function of x and y dy equals 0. This equation is exact if the partial of m with respect to the other letter, dy, is equal to the partial of n with respect to the other letter, not y, but x. Okay, so that differential equation is exact, and now it has to equal 0, is exact if the partial of m with respect to y equals the partial of n with respect to x. Now, notice that that says x and that says y. With respect to our alphabet, x comes before y. And over here, I have m and I have n. M is, so if we have something like this, 3x plus 5 dx plus 4y, I can have 5y there, 4x minus 2x plus 11 dy is equal to 0. Just like in the alphabet, x comes before y, and I don't mean that I'm writing x first. What I'm saying is m is with x and n is with y. That is, when it comes to x and y, x is before y, and when it comes to m and n, m is before n. The earlier letters are teamed up. That is, you have m times dx plus the latter letters are teamed up. You have n times dy, just like it says up here. So whatever x dx is being multiplied by, whatever dx is being multiplied by, we call it m. Whatever dy is being multiplied, we call it n. So now, if you have that dy dxa is equal to 3x plus 4 times y, I can get this to look like what I'll call standard form. I can get it to look like this. I can get it to look like this. The first thing I will do is, well, I'll move pieces around. In fact, let the y be in the bottom. That's a 4. I move the pieces around. It's like check this a little bit. I'll move this up here. I'll move this up here. Now I have y dy is 3x plus 4 dx. And I'll move one equation to the other side. Minus 3x plus 4 dx. So I move this to the other side of the equal sign. So the right hand side is now 0. With respect to the alphabet, x comes before y. So this is m, because m comes before n. That's how I remember which to call m and which to call n. Now we're going to solve a differential equation. using this technique plus more. This technique that I showed you just shows whether or not the equation is exact. I happen to write x first, so that's m and n. I look at the partial of m with respect to not x, but y. That is, I take the partial of n with respect to y. With respect to y, the derivative of that is cosine of y minus. With respect to y, the derivative of that, well, that's just a constant times y. Y times sine x is sine x times y. The derivative is just the constant. Sine x, when we're taking the partial with respect to y, the constant. Okay, now let's look at the partial of n with respect to not y, but x. Take the partial of this. With respect to x. So we do it term by term. With respect to x, the derivative of cosine x is negative sine x minus. Now we have x times a constant. Cosine of y is a constant. With respect to x, the derivative of x times that constant is just a constant. Minus the derivative of y. For y is a constant because we're taking the derivative with respect to x. The derivative of y is 0. And the rule for taking away 0 is don't even bother. And then you say, yes, these two are equal. Oops, they don't look equal. So let's see what just happened. They don't look equal. Okay, and the reason they don't look equal is because n had her plus sign right here. So this just should have been plus always. And the derivative of x times the constant is just a constant. Now they really do look equal. So now we verify that it's an exact differential equation. What is it? This here is an exact differential equation. Now I'm not going to go into this theory about why what I'm going to do works. That's not what the purpose of this video is. Go and read your textbook. But basically, this piece here is df dx. And this piece here, including the sign, if that was a minus, then n has the minus sign. Be aware of that. This is df dy. Now, our goal is to solve for f and set it equal to c, a constant. So, if df dx is equal to what I underlined, sine y minus y sine x. Now, I could have started off right here. I could have said that df dy, or partial f partial y, is equal to n. I just did it. Now I integrate both sides with respect to x. I integrate both sides with respect to x. You can think of that canceling out. The integral of df is just f. Integrate the other side. This is a constant, the integral of a constant times dx is just x times the constant minus y is a constant. The integral of sine of x is negative cosine of x. Now, so I'm going to check to see that I did this right. I'm going to take the partial of f with respect to x. So you have x times a constant. The derivative or partial derivative will just be the constant plus y times the derivative of cosine x, which is negative sine x. And I got exactly what I had up here. This works. But every time you integrate, as you know, you get a constant. Now this constant, since I integrated with respect to x, or when I differentiate, I'm differentiating with respect to x. And no matter what I put here, when I differentiate, I better get this. I better get that. Now, if the constant is a function of y, then when I take the derivative of it, it's just going to be 0. So the constant of integration is, we'll always call it the g function, is g of that other letter. If I'm integrating with respect to x, then I can have a function of y. Now, I know that when I take the partial of f, and f is right here, with respect to y, that I'm going to get two answers. One of them is going to be n. One of them is going to be cosine x plus x cosine y minus y. I almost lost that x here. Okay, now what is the partial of f with respect to y using this rule up here? Well, x is the constant this time, times the derivative of sine of y, which is cosine of y, plus, now cosine x is the constant, times the derivative of y, which is 1. Multiplying by 1 you don't have to bother with. Plus, let's say plus, the derivative of that with respect to y. That's g prime of y. Now, you should have lots of things canceling out, like plus cosine x and plus cosine x, and plus x cosine y plus x cosine y. So we have that g prime of y is equal to negative y. Integrating both sides, the integral of g prime of y is g of y. The integral of the other side is negative y squared over 2. Okay. So at this point, we're pretty much done. All I'm going to do is take this equation here and substitute in what g of y is. So f is equal to x sine y. For now, I'm just copying, plus y cosine x plus g of y. For plus g of y, those two symbols tell me whenever I see plus g of y, I could erase it and put negative y squared over 2 minus y squared over 2 equals a constant. This here is the solution to the differential equation. That is the solution to this differential equation. Now, let me copy it down and let us prove that this is exactly right. I claim that x sine of y plus y cosine of x minus y squared over 2 equals c. This is the solution to this differential equation. Now, who knows? Maybe I'm crazy. Maybe it's not true. Okay, let's solve this equation for dy dx. And the first thing I can do is divide by dy by dx. So I get the sine of y minus y times the sine of x plus this mess times dy over dx is equal to 0. Now remember, if you have a times b over c, this is a times b over c. And the quick argument is, I know some people like to put a 1 here, but either way, a times b is exactly what I have here. Personally, I just like to say c's in the bottom. If you want to say 1 times c, fine. And that is what we have. 1 times c is c. Now, all I'm going to do is bring this to the other side. So I have this piece, cosine x plus x cosine y minus y times dy dx is equal to, I'll put, when I bring it over as negative, it becomes this. And then I divide by this mess. Cosine x plus x cosine y minus y. This, first let me get rid of this. The given differential equation, this differential equation is 100% equivalent to this. So that's what I want to show. I'm going to take the derivative of my solution, which is in the top right, and I want to get that dy dx is, just like I said it was down here, y sine x minus sine x equals cosine x plus x cosine y minus y. So we're taking the derivative with respect to x. So every time you take a derivative of y, you get dy of y term, you get dy dx. This is a product. So I take the derivative first, which is 1 times the second, plus the first, which is x, times the derivative of the second. The derivative of sine of any angle is cosine of that angle times the derivative of the angle, which is dy dx or y prime. That is the derivative of the first term, plus the derivative of the second term. Product rule. The derivative of y is y prime times the second function, plus the first function times the derivative of the second, which made this negative, because it's negative sine x, minus the derivative of that is y times y prime, and it equals to the derivative of constant, which is 0. So now this term and this term and this term all have y prime. So I'm going to bring everything else to the other side. I'm going to bring this to the other side, and I'm going to bring an understood plus sine x, plus sine y to the other side as minus sine y. And everything that is underlined in blue has a y prime. So I can factor it out. I have x cosine of y, y prime, plus cosine of xy prime minus y prime. And then it's simple. Divide both sides by what I just crossed off. And just to save a little time and space, what I'm erasing is just y prime. I'm just going to put it closer. And unless I made some silly error, what I just boxed should be this. And it is. Maybe these two terms were interchanged, but they're equal because addition commutes. I can say this plus that, or I can say that plus this, like I did down here. But they're equal. Let us try another differential equation. Suppose that you are told that 2y minus 1 over x plus cosine of 3x times dx, times dy dx plus y over x squared minus 4x cubed minus 3y sine of 3x is 0. Now, when I see a function like this, I think exact, because, just give me one little moment, please. I think they're exact because if I multiply each term by dx, and terms are separated, at least on either side of the equal sign, by addition and subtraction signs are not inside parentheses. This is the term separator. It's this term times this term, and the right side is just one term. Now, if I were to multiply the first term by dx, this cancels. And if I multiply the second term by dx, I get that. If I multiply 0 by dx, I still get 0. So rather easily, you can get this into what maybe we'll call standard form. Remember, x is before y, and m is before x. M is before n, excuse me. So I'm going to call this m, not the dx, and I'm going to call this n. Now, the partial of n with respect to not y, but the other letter. Well, the derivative of 2y is 0, minus the derivative of 1 over x is minus 1 over x squared. Don't need that plus in front. Plus the derivative of cosine of any angle is negative the sine of the same angle times the derivative of the angle. Okay, wonderful. Now, does this equal to the partial of m with respect to not x, but y? Well, the 1 over x squared is a constant. Remember, this is the same as 1 over x squared times y. And the derivative of constant times y is just the constant. Minus. That's the constant. It has no y's in it. Its derivative is 0. I won't even bother writing it down. Minus. Only the y is not a constant. This here can be thought of as 3 sine 3x, a constant, times y. And I take the derivative of that with respect to y, I just get the constant. They both have a positive 1 over x squared. They're both taking away 3 sine 3x. And that's all they're both doing. It's no longer a question. They're equal. which means the top differential equation is exact. So now that we established that it's exact, now on an exam, do not erase what I'm doing, keep it. Now I need to solve for f. Remember, this is the partial of f with respect to y. And m is the partial of f with respect to x. Now using those two pieces of information, we can uniquely, well up to a constant, we can find f. Now, we know that df dy is equal to 2y minus 1 over x plus cosine of 3x. Integrating with respect to y, this will just become f. Integrating this with respect to y will be y squared. After all, the derivative of y squared is 2y. Minus, this is a constant. The integral of a constant with respect to y is the constant times y. Plus the constant with respect to y. When I integrate that, I get the constant times y. Plus any function of x. Now remember, when I take, if I did it right, when I take the derivative of that, with respect to good old y, I will get this. But now, even if I add on the g of x, g of x is just a function of x. Maybe it's 3x cubed plus 4 ln of x minus e to the 3x plus 11. When I take the derivative of that with respect to y, I'll get 0. So when I go backwards, if I take the partial of this with respect to y, the g of x just becomes 0. So it can be any function purely in x, no y's. Okay, now, this is f. I'll take the partial of f with respect to x. When I do it here, that's the constant. When I take the derivative, it becomes 0, minus y is a constant, so it stays, and the derivative of negative 1 over x will become plus 1 over x squared. Plus, the y is a constant, this y is a constant, the derivative of cosine of 3x is negative the sine is 3x times the derivative of 3x plus the derivative of g prime of x. That's on one hand. On the other hand, we are given df dx, partial f partial x. It is y over x squared minus 4x cubed minus 3y sine 3x. And if we do this right, lots of things are going to cancel. Definitely things that have y's in it. Like y squared over 2 cancels, minus 3y sine 3x, they cancel, and what's left should just be functions of x. G prime of x is negative 4x cubed. Integrating the left side gives me g of x. Integrating the right side, get negative x to the 4th. If you don't believe it, just take the derivative of that and say, yeah, it's negative 4x cubed. So now, all I do is I update this equation. I erase plus g of x, and I put in minus x to the 4th, equal a constant. That is the solution. Not every time can you solve for y. Now just for the record, you should always try to. For the record, if the y squared, if this y squared was not here, if I just had negative 1 over xy plus y cosine of 3x minus x to the 4th is equal to a constant, you can solve for y. For example, this term and this term has y, and I'll bring that to the other side. So by design, I can factor out the y. And this will equal to x to the 4th plus c. If I divide by this, I'll have my answer. I'll have that y is equal to x to the 4th plus c over, looks like negative 1 over x plus cosine 3x. I'm not going to do this, but maybe you should multiply each term by x, so that x will disappear. But I'm not going to do it because that wasn't even a solution. This is not the solution. The solution to this differential equation is right here. Y squared minus 1 over xy plus y cosine 3x, excuse me, minus x to the 4th is equal to a constant. Always more. Suppose you have 1 plus ln of x plus y over x times dx. This is equal to 1 minus ln of x dy. Now this is not in standard form. If I bring this to the other side, it'll just become minus that, and it now equals 0. So if I bring everything from the right side over to the left side, the right side is 0. Now, I don't stress over whether I have dx first and dy. I just remember x is before y, just like m is before n. So the dx, we call what's in front of the dx m, and we call what's in front of the dy n, including the signs. Now, if you want, you can say negative 1 minus ln of x is plus ln of x minus 1, and you can even put a plus sign in front. If that's your style, go for it. So the question is, and has always been for these problems, is to solve this differential equation. But first I want to find the partial of m with respect to not x, but y. That is, I want to find the partial of this with respect to y. Well, let me finish. With respect to y. Well, the derivative of 1 is 0, plus the derivative of ln of x is also 0. 0 plus 0 is 0, plus, remember, 0 plus whatever is just the whatever. So I'll just write down the derivative of that. The derivative of plus y over x is just 1 over x. Just remember, y over x is 1 over x times y, and the derivative with respect to y. The 1 over x is a constant, the derivative of y is 1. So you just get the constant. Alright, now what about the partial of n with respect to the other letter? What's the partial of ln of x minus 1 with respect to x? Well, the derivative with respect to x of ln of x is 1 over x. Minus the derivative of 1 is 0. And taking away 0, don't bother. Oh, look at this, folks. We got the same answer. So this top equation is exact. That top equation is exact. So let us just remove. So now on an exam, for example, you really should say equal, which implies exactness or exact. Let your teacher know that you didn't just calculate the partials and not even know that they were supposed to be equal. To continue. Later on in this section, we'll talk about how to solve non-exact differential equations. Okay, so now we have that it's exact, and this here is a partial of f with respect to that, and n is the partial of f with respect to 1. Now, up to now, I've always started off with this equals that. I'll start off the other way. df dy, partial f partial y, is ln of x minus 1. If I integrate with respect to y, that will just give me f. Now this is a constant. Ln of x is a constant. I integrate it with respect to y, I get that constant times y, minus 1 times y. The integral of 1 with respect to y is y, plus any function of x. Because to double check that this is right, you would take the partial of that with respect to x, and you would check to see if you get this. And assuming we did this part right, we would get ln of x minus 1 plus the derivative, with respect to y. I'm so sorry. Just like it said over there. The partial of this with respect to y is 0. So here I do get it back. Now what do you do next? Well, since you took the partial with respect to y of f, now I'll take the partial of f with respect to x. Y is a constant. The derivative of ln of x is 1 over x minus y is a constant. Its derivative is 0 plus function of x. Its derivative is g prime of x. That's on one hand. On another hand, we are told what df dy is. It's this. It's 1 plus ln of x plus y over x. And definitely the terms that have y's in them are gonna cancel out. So now we have positive g prime of x is 1 plus ln of x. I integrate both sides with respect to x. The integral of g prime of x is g of x equals. The integral of 1 is x. The integral of ln of x, that's a whole nother story. What is the integral of ln of x dx? Well, this we're going to do by parts. I know how to take the derivative of that, but not the integral. Remember, if you need another factor, you can always say I'm multiplying by 1. So I'm going to let u equal ln of x, and dv is what's left over. 1 dx, or if you prefer, just dx. Now, the differential of ln of x is dx over x. And if dv is dx, then v is x. And the formula is uv minus integral of v du. Now u times v, which is the same as v times u, there's v times u. If you write u times v, some people might think of that as ln of x squared, as opposed to just ln of x times x. Okay, so you put their x in front, and you'll never make a mistake as to what you're taking ln of. Minus v du. Well, that's v, and that's du. And when you multiply them, the x's cancel out, and you just get dx. But that's a simple integral. The integral of dx is just x. Okay. So I take this answer, and I put it in the bottom here. I took the integral of 1, I got x, plus the integral of that is x ln of x minus x. Coincidentally, plus x and minus x canceled out. So you just get plus x ln x. That is what g of x is. So this here was side work to solve for g prime, or g of x. Now, instead of g of x, I'm going to put x ln x. Instead of g of x, I'm going to write x ln of x, and this is equal to a constant. And this here is the solution to the differential equation. Now, just to keep as much on the board as possible, I won't go to a new page. I'm going to write down this solution, and I'm going to look at it a little bit carefully, and I'm going to say, yeah, this time I can solve for y. These are the three terms on the left side of the equal sign, and that's their one term on the right side of the equal sign. Notice, it's simple. The terms are separated by addition and subtraction signs. Now, just remember that this y over here is being multiplied by 1. So when I factor out the y, I'm going to bring this over to the other side. I only have terms that have y's on the left side now. And then I write down everything but y, which is in red. It's ln of x minus 1. So y, dividing both sides of the equation by ln x minus 1, y is c minus x ln x over ln of x minus 1. Now, some people might think this means that. So you can make it really clear. Or, for the bottom, you can say negative 1 plus ln x. Nobody will think that you're taking ln of x minus 1. But even without the blue, there's your answer. Y is equal to this. And you can take the derivative and make sure you get the right answer. Number 4. Maybe in this case, we'll actually do this. Suppose you have 3x squared y plus e to the y dx plus x cubed x e to the y minus 2y dy. This is 0. X is before y, so this must be n, because m is before n, and that's n. The partial of n with respect to not x, but the other letter, that is the partial of 3x squared y plus e to the y partial y. Well, the derivative of 3x squared y 3x squared is a constant. And a constant times y, its derivative is just a constant. Plus, the derivative of e to the y is e to the y. Does this equal to the partial of n? I'm sure that's a typo. It's x cubed plus x e to the y minus 2y. When I take this with respect to x, well, the derivative of x cubed is, of course, 3x squared plus x times a constant. The derivative is just a constant. That is, it's 3x squared plus e to the y. 3x squared plus e to the y minus the derivative of 2y is a constant. It has no x's in it. So it's going to be minus 0. Oh, yeah. These are equal. They are equal. So it is exact. Okay. So now that it's exact, we play the game. This here is the partial of f with respect to x. And this is the partial of f with respect to y. So partial f, partial x is 3x squared y plus e to the y. If I integrate with respect to x, this will just give me f. If I integrate with respect to x, this 3y is a constant. The integral of x squared is x cubed over 3. And the 3's cancel. Plus, this is a constant. When I integrate it with respect to x, I get x times the constant. Plus some function of the other letter, g of y. And like I said, those 3's cancel. Now I take the partial of f. Well, I've already taken it with respect to x. Now I take it with respect to y. Or, I didn't really take any partial with respect to y, x with respect to x. I just wrote it down, okay? So now I'm going to take the partial with respect to y. X cubed is a constant. The derivative of y times a constant is just a constant. Plus, x is a constant, it stays. The derivative with respect to y of e to the y is e to the y. Plus, that's a function of y, its derivative is g prime of y. And we know what df dy equals, partial f partial y equals. It equals this stuff, including the plus sign. It equals x cubed plus x e to the y minus 2y. Well, the x cubed goes, the plus x e to the y goes, and what we have left is that equals this. G prime of y is negative 2y. Integrating, we get g of y is negative y squared, or plus g of y equals negative y squared. These two horizontal lines mean wherever I see plus g of y, I can put negative y squared. Okay, plus g of y is gone. What comes in? Minus y squared equals a constant. Here is your solution. And yes, absolutely, you should write that underneath. Obviously, I ran out of room. Let's try one more. Okay, now this one is going to be non-exact. It's not going to be exact. you have 5y minus 2x times dy plus 2y times dx equal to 0. This is n, this is n. The partial of m with respect to not y but x is going to be negative 2. And the partial of n with respect to not x but y is just going to be 2. And they're not equal. They're not equal. Now, we want to find something called an integrating factor. And there are two ways of doing it. M sub y, partial of m with respect to y, minus n sub x. Since I wrote m first, I divide by m. Now, we want this to be a function of x, to be our integrating factor. If it isn't, then I reverse the numerators. I put nx minus my. Now notice that, I do have one typo here. N is second, that's what you divide by. I have m sub y, m is second, I divide by m. And I want to see if I just get a function of y. Now, it turns out that this is my. My is a shorthand for dm partial n partial y. This is a shorthand for partial n over partial x. Okay? So I have my and mx. So this one's going to give us my minus nx, which is 2, divided by n, which is 2y. So I get negative 4 over 2y, which is negative 2 over y. Over here, nx is 2, minus my is negative 2 over m, which is 5y minus 2x. So here I get 4 over 5y minus 2x. And we didn't need to do both. I just want to show you something. And unfortunately, I even had a mistake. Sorry. Is this a function of y? Oh, it is. That is our we're going to use this to calculate our integrating factor. If you tried this one first, this is not a function of just x. It is not a function of just x. It's a function of x and y. How do you know if something's a function of x and y? You just ask yourself, for you to give me an exact value for this, what will I have to tell you? Well, I'll have to tell you what y is. Y is 3. X is 11. Now you can tell me exactly what this is. It'll be 4 over 5 times 3, which is 15, minus 2 times 11. It'll be 4 over 15 minus 22. Negative 4 over 7. I can tell you exactly what this is if I tell you what x and y are. That's not a function of just x. Now, how do you know if you want it to be a function of x and y? Well, if y is first, you want a function of y. If x is first, you want to get a function of x. And then whatever letter comes second, that's what you divide by. So if you did this first and you did not get a function of x, then you should come and do this. And then you say, yep, it worked. I got a function of just y. So now the integrating factor. Now what we're going to do is we're going to multiply both sides, which means all terms, by the integrating factor. The integrating factor will look familiar. It's e to the integral of this dy in this case. Now what is, so it's going to be e raised to something. What is the integral of negative 2 over y dy? Well, if you factor out the 2, you get the integral of dy over y. Well, I know that integral is ln of y. Negative 2 times ln of y. But that negative 2 can go up as the power. So the integral is ln of negative 2. ln of y to the negative 2. So it's e to the integral, ln of y to the negative 2. But e to the ln of anything is the anything. That is our integrating factor, y to the negative 2. So the integrating factor is y to the negative 2, or 1 over y squared. So as promised, we're going to multiply this differential equation at the top by the integrating factor. 5y minus 2x. We're going to divide it by y squared. That's the same as multiplying by y to the negative 2. So you get 5 over y minus 2x over y squared. You get 5 over y minus 2x over y squared dy plus, now if you take 2y and you multiply it by y to the negative 2, or you multiply it by 1 over y squared, you get 2 over y dx. Now, equals 0. This, because 0 times anything is 0. This differential equation has the same solution as the one above. It has the same solution as the one above. But this one's exact. Now, I would advise you to confirm that. That way you know you didn't make any silly mistake. What is the partial of 5 over y minus 2x over y squared with respect to not y but x? Well, that's a function just of y, it's 0, minus, it's that constant times x. So it's just going to be the constant. Now, let's take the partial of this. The partial of 2y with respect to not x. Okay, now, when you had 2y and you divided it by y squared, you got 2 over y. Somehow I did not write that. Sorry. 2 over y dx. So the partial of 2 over y with respect to y, that's negative 2 over y squared. Make sure you can get that. All I did was take the derivative. 2 over y, derivative is this, 2 over y is the same as 2y to the negative 1. We bring down the power, multiply it by the 2, make the new power 1 less, get negative 2 over y squared. Yep, they're equal. So we do have an exact differential equation. Now, personally, this function looks a lot simpler than that function. So I'm going to call that df dx. And including that sign, there was a minus. Include that df dy. So if df dx is equal to 2 over y, that would imply integrating with respect to x. When I integrate this, I just get f. When I integrate that constant with respect to x, I get 2 over yx plus a constant of integration, which can be a function of y. Because when I take the derivative, when I go back, the derivative of that function of y will be 0. Now I take the partial of this, not with respect to x, but with respect to y. df dy. So 2x over y is the same as that. And when I take the derivative with respect to y, that's my constant. When I multiply by -1, I get negative 2x y to 1 less. And negative 2x over y squared. Negative 2x over y squared. Plus the derivative of g of y is g prime of y. Which, we know what it's supposed to equal. We know what df dy equals. It equals to this. Sorry, it equals to this. It equals to 5 over y minus 2x over y squared. Well, look. The minus 2x over y squared cancel. And what survived is this. G prime of y is 5 over y. Integrating, you get g of y is 5 ln of y. So I'm going to update what's in this red box. And I'm going to tell you f, which is a function of x and y, is equal to 2x over y plus g of y. But g of y is 5 ln of y equals some constant. This is the solution to the differential equation from the very, very top. The same solution. So you calculate the integrating factor, you multiply everything from the original equation by the integrating factor, get it in standard form first. First get this in standard form, which it is in. See that it's not exact. Calculate the integrating factor, and then multiply the whole equation by the integrating factor, and here it is. And then solve it like usual, like you do all exact differential equations. And I lied, we'll do one more. Suppose you have xy dy plus 2x squared plus 3y squared minus 20 dy is 0. X, sorry, that's it. Now one of these has to be wrong. That says x. If that's x, then that must be m. If that's y, that must be n. So let's see if it's exact. If it isn't, we make it exact. The partial of xy with respect to not y, but the other letter, well, that's y. Because if x times a constant, the derivative is the constant. The partial of m with respect to not x, but y, this is just going to be 6y. Because this term and that term are constant, so its derivative is 0. And we all know the derivative of 3y squared is 6y. They are not equal. Okay, so now we need to do the integrating factor. N sub y minus m sub x. I wrote m second, so that's what I divide by. And I wrote n sub y first. Is this a function of y? Well, I have ny. It's just y minus, here is my, it's 6y. Now, once you calculate that, you should start thinking. The top is just y's, negative 5y. Now, if you did it the other way, then you have to divide by n. But the top is going to be similar. It's just going to be 6y minus y. It's going to be plus 5y. That is, it's just y's. So I want to divide this something that has y's in it. I want to divide it by something that has just y's, or just, it has a y factor. It has a factor of y. This has a factor of y. That is, whether, so what's that? That is n. So if I divide by xy, I can kill off the factor of y, and I just get 5 over x. Okay, and this is fine. This is exactly what we want. In fact, earlier on, let me just look at something, please. Okay, so over here, I just made a sloppy mistake in copying. This is my minus nx. Just alphabet soup. Now, again, I did it wrong. mx minus ny. I want it to be a function of x, and it is. So we're going to use that to calculate our integrating factor. The integrating factor is going to be e to that integral. E to the integral of 5 over x dx. So the integral of 5 over x dx, I can pull out the 5, and I just have the integral of 1 over x dx, or dx over x. In either case, it's ln of x, which is ln of x to the 5th. So this integral is ln of x to the 5th. So I get e to that integral, which is ln of x to the 5th. So e to the ln of anything is the anything. So that is my integrating factor, x to the 5th. Integrating factor is x to the 5th. So now it's a brand new problem, or it's almost a brand new problem. First, I'm going to multiply by x to the 5th. So I'll get x, when I multiply this by x to the 5th, get x to the 6th y dy, plus, when I multiply this by x to the 5th, I get 2x to the 7th, plus, when I multiply this by x to the 5th, I get 3x to the 5th y squared, minus, when I multiply this by x to the 5th, get 20x to the 5th. I multiply this factor by x to the 5th, so I don't have to multiply that by x to the 5th, equals. When I multiply that by x to the 5th, I get 0. This is an exact differential equation. You can verify that it's exact See that the correct partials are equal to one another. Now, this is partial f with respect to y, and this here is partial f with respect to x. Now the first one looks real simple looking. So df dy is x to the 6th y. If I integrate with respect to y, with respect to y, the integral of that is just f, and the integral of this, well, x to the 6th is a constant, the integral of y is y squared over 2, plus a function of not that letter, but x. Now I take the partial of both sides with respect to x. The partial of f with respect to x, well, that's partial f, partial x. The partial of the right side with respect to x, that's the constant, times the derivative of the function of x, which is 6x to the 5th, plus the partial of that with respect to x is g prime of x. All I'll say is that 2 goes into 6 3 times. That's 3y squared x to the 5th. 3 times y squared times x to the 5th. Plus partial plus g prime of x. That's on one hand. On the other hand, I know what partial x equals. It equals to this. It equals to 2x to the 7th plus 3x to the 5th y squared minus 20x to the 5th. What I realize is that plus that and plus that are on both sides of the equation, so they cancel. So g prime of x is equal to what survived. 2x to the 7th minus 20x to the 5th. Integrating both sides, get g of x equal to the integral of that, which is 2x to the 8 over 8. But 2 over 8 is over 4. Minus 20x to the 6 over 6. 20 over 6. I divide the 20 by 2 and divide the 6 by 2. And I get that. Okay? So I come back to g of x. So really I write it down underneath. And then I add on what g of x is. X to the 8 over 4 plus 10x to the 6 over 3. I just wrote down what g of x was. Equals a constant. Here is the solution to the differential equation. And this completes the section on exact and non-exact differential equations.